Good afternoon. My name is Richard Chrysler, and I'm here to talk to you today about experiment 510. So this 500 series experiments, whether it's 510 or 520, are both level control experiments. Now, there's another video that's made for experiment 520, and that was made by the laboratory teaching assistant, Robert Wandell, and that will be actually a separate video. This one that I'm making is going to be specifically for experiment 510. But whether or not you're assigned to do experiment 510 or 520, you need to watch both videos because you will actually use both sets of equipment. Okay? So if you are slotted to do experiment 510, the first hour and a half of the lab period you will start with this apparatus. Then the second hour and a half you will work with experiment 520, which is the lab volt level control system. And again, that video was done by your TA, Robert Wandell. So let's talk a little bit about experiment 510. Both experiments are similar in the sense that they're both level control experiments. On experiment 520, you have a variable speed pump that you will use to control the level. Here, you'll have a proportionating valve that you will use to control the level. Now this type of valve here is something like you would see in industry. We have a compressed air supply that supplies air to a regulator, which is actually an electronic pressure regulator, which is exactly the same regulator, same type of system that's used on experiment 720, the 700 series. So this regulator receives a 4 to 20 milliamp signal and then increases or decreases the pressure inside this chamber, which then causes the valve stem to either go up or down. So either shutting off the flow or increasing the flow. Now the way this valve works is that if it receives no signal no signal from the controller, no control signal, it's all the way open, which is exactly opposite of the multi-tank discharge experiment. The control valve used on that experiment with no signal it is all the way closed. So this is the exact opposite. And so we have the water supply feeding into the control valve, and the outlet goes through the rotometer. It's important to make sure that this rotometer the valve is open all the way. So the flow rate that's being generated is only being generated by the signal supplied to the pressure, the regulator here. And so what we have is that I have the outlet open a fixed amount. So depending on how high the water is in the tank, you get a variable flow coming out. And then I also have a disturbance variable that will be set. So please do not change the setting of this valve. To introduce the disturbance, what you will do is you'll open this ball valve here to either allow flow out or to stop the flow to remove the disturbance. Now this has been set up so that you will not adjust anything on this variable power supply. So if you look at the video for the process measurement experiment where you were manipulating V1, the voltage 1 output here, don't touch this at all. When you come on, it should be on, and it should display 10 volts on here. That's the excitation voltage for the differential pressure transducer, which provides your measurement for this experiment. And so, to manipulate our controller for these process dynamics experiments, we have to use the configuration program that you have access to on Blackboard. And all of you wrote an initial configuration program for your process measurement experiment. And here I provide you, for this experiment, I provide you a little bit more information in the worksheet so you have a better understanding of how to input the correct values into your configuration program. But primarily we're going to be concerned with two screens here. The first screen will be output 1, where we're going to change proportional band settings, the reset setting, which is actually the integral settings, and the rate we're going to have set to 0 for the entire lab period. We're not going to mess with the rate at all. That's the derivative setting. So for PID control, you've got the gain or proportional band, you have the reset time or reset rate, and then you have the rate, which is just the derivative, so Pi and D. And when you come into lab, the system will already be at some steady state, and depending on the lab instructions, which I'm going to write up at the end of the day today, it'll be very clear what you need to change first and what order, what you need to change first, second, and third. But essentially, you'll be changing different combinations of the proportional band, the reset time, and the set point, doing step changes in the set point value. And you'll also be introducing a disturbance and watch the system respond to the disturbance. Now the bad news is that these controllers are not set up to send data to the computer at this time. I hope to have that problem resolved here in the near future, but for now you should plan on either recording data by hand or having a phone or a video recorder and basically recording the change in the input variable with time after you make the step change. And what you'll need to do is you need to keep very careful notes about what video corresponds to what change in your data. So that's going to be very important because you'll be at home trying to figure all this out, and if you don't have good notes, you won't be able to figure it out. So that is one downside to this particular experiment. But if we go here, the outputs, and you can change to make a change in any of the settings. You go ahead and enter the change. Sometimes you'll get a warning saying, "You sure you want to do this?" And you just say, "Okay, yes, I do." But now once you make the change here, the controller does not have that change in memory yet. So what you have to do is send it from the computer to the controller. You do that with the right feature here. And then you say serial port. And it's going to prompt you to say, "Are you sure you want to do this?" You just say, "Okay, okay," all the way through. And then it will go ahead and send that information to the controller. It'll reset it. And as you can see, the system will initiate some response based on what I told it to do. Now, depending on what I told it to do, it might change very quickly, or it might change very slowly. But that's something that you're going to be interested in looking at when you come to do your experiment. Now, you can see that the level is dropping. So whatever I told it to do caused the level to drop. And you'll get a chance to see what happens when you just change proportional band settings, or if you introduce a disturbance and then reduce the disturbance or eliminate the disturbance where it goes back to some steady state value. And then what happens when you use the integral setting, when you change the integral setting from a high value to a low value, and you'll see how the process responds. But again, it's going to be very important that you do the changes in the order that we're going to tell you to do in the lab instructions. And then if you have time left over in the end, you can do additional trials with different combinations of variables as you would like. But we'll also give you kind of a range of, so proportional band range. So we'll say, yeah, you can change the proportional band from this value to this value, the integral setting from this value to this value. And basically what you want to do is see what happens if you have a high proportional band or a low proportional band, a high integral time or a low integral time. And what happens when you have a disturbance, how long does it take to get back to some steady state? And so kind of what we came up with was because I know that's going to be a big question, how long is it going to take for a system to reach steady state? Well, we're still exploring that, but to give you a rough idea of what we're looking for is you watch the measured value change, and then once it gets to a reasonably stable value and stays there for 1 minute, that's what we're going to call the steady state. So it may oscillate up and down a little bit, or it may be perfectly steady. Like right now, that looks pretty steady to me, so that's good. And you can see it didn't take very long. It took maybe a couple of minutes to do that. But once it stayed at this value, and again, it might oscillate up and down a little bit, like a tenth of a degree or a tenth of a centimeter or whatever. But as long as it stays there for about 1 minute, we're going to say that that's essentially a steady state. You can plan that it's going to take maybe 5 to 10 minutes, but it may respond a lot faster than that. So just keep that in mind when you're planning for your trials, and please let us know if you have any questions. Thank you very much.